So hi, my name is Siddharth Suresh. I'm a senior software engineer at the SDF, and today I'll be speaking about the work we put into scaling Stellar Core. So our main goal is to ensure that we stay ahead of block space demand. In the past, we focused on network-related scalability improvements, such as efficient transaction propagation and aggressive load shedding. But earlier this year, we launched Soroban, and Soroban transactions are a lot more expensive, or can be a lot more expensive in terms of networking and CPU demands. However, Stellar Core does almost everything on the main thread. So to give you an idea, classic transactions are typically small, a few hundred bytes, and are typically fast to apply. And I say typically because in some rare cases when there's a lot of DEX activity, even classic transactions can take a while. But most of the time, they're cheap to apply. Soroban transactions, however, can be hundreds of kilobytes large due to WASM size. And they are also slower to apply because smart contracts allow arbitrary code execution. The network has an upper bound on the amount of execution expressed through the network limits, but we want to be able to increase this. These transactions create a new burden on CPU. So as Soroban usage is ramping up, we don't want to end up here. We don't want to end up in a situation where we're using one CPU to its limits, and the other cores are just sitting idle. So the main goal of this talk is to discuss parallelization efforts in Stellar Core. This image is also what we don't want. So of course, this idea is not without some challenges that we're facing here. The first challenge is that Stellar Core is a 10-year-old code base, and most of its components aren't parallelization friendly. So making any parallelization changes require fairly significant overhauls of core subsystems. In addition, the Stellar network is fully functional and stable and has been for years. So shipping major changes like this one has to be done very carefully. The second challenge is that most of Stellar Core is written in C++. And to understand why this is a challenge, here's a quote from our colleague of ours, Graydon, the creator of Rust. Graydon says that a significant motive for Rust existing in the first place is that multi-threaded C++ is just extremely hard to make correct, at least without strong restrictions on any data shared between threads. Essentially, when writing multi-threaded code, the language does not help us at all in terms of safety. So it is really easy to end up with problems like data races or deadlocks. There is hope, though. Soroban is in a much better place, as it was designed to be parallel-friendly. This is due to transaction footprints. Transaction footprints specify which ledger entries are going to be touched by a transaction, which allows for the partitioning of transactions into conflict-free sets. And as a result, the parallelization code is simpler and safer. So now that we know what the challenges are, let's go over a quick overview of what happens in core during a single ledger on the network. And the way to think about this is that there are essentially three streams of work. The first is that we propagate new transactions. New transactions enter the network continuously and need to be propagated to validators. Every Stellar Core participates in this propagation process. The second is that we vote on blocks through the Stellar Consensus Protocol. The Stellar Consensus Protocol requires validators to exchange messages with other validators that they trust. So this stream of work involves validators voting themselves, as well as helping propagate votes of other validators. And finally, we need to apply the confirmed blocks to the database. When the network agrees on a block through the Stellar Consensus Protocol, Stellar Core applies the block to the database, and at that point, the block is confirmed. The transactions in the block are confirmed. There are opportunities for some of this work to run in parallel. So before diving into these opportunities, let's visualize the ledger flow first. So the arrow here is our main thread. And above this arrow is all the work that Stellar Core needs to do in order to confirm a ledger. It has to run the Stellar Consensus Protocol and exchange votes with other validators on the network. And those are the blue rectangles on the left that say vote. And it also needs to process and propagate new transactions on the network. And these are the yellow circles. And once SCP is done confirming a block, it actually needs to apply those transactions to the database. And those are the purple rectangles. So if we were to place all the work on the main thread, it would look something like this. Ledger n and n+1 are time markers. And as you can see, it's quite busy. So what can we do to improve the situation? First, let's make some observations. The first observation is that transaction propagation can actually run sort of independently of consensus and block application. And I say sort of because, of course, new transactions are needed to construct and confirm blocks. But when voting an application occurs, transactions for that block have already been received. New transactions for that block, new transactions received during voting are essentially transactions to be considered for the next block. So processing of new transactions, the yellow circles, is a bit independent of voting and application. Today, transaction propagation and voting share the main thread, causing head-of-line blocking issues. So what this means is that a delay in processing a transaction causes a delay in SCP voting. And voting is latency sensitive, so a delay on one validator may impact global latency of the Stellar Consensus Protocol. Another observation is that block application typically takes a significant amount of time. On our own validators, we see numbers between 300 milliseconds and 1 second. Of course, occasionally there are outliers where application takes much longer, but typically application is under 1 second. So, and we expect these numbers to grow, if you recall, that Sorbonne transactions are more expensive to apply. So we have the same head-of-line blocking issues for SCP votes, but it's actually even more dramatic here because apply time takes a while, so everything has to wait. And the last observation is that consensus requires the most up-to-date state to produce valid blocks, which means voting and application should remain sequential. Note that this means that Stellar Core itself can't issue its votes, but it can still receive, process, and propagate votes from other Stellar Cores. So it is possible to pipeline voting and application and start voting for ledger n+1 while ledger n is being closed, but it requires changing how blocks are constructed. In the first iteration of this work, we're not doing that yet, but we're planning to in the future to truly make voting and application parallel. So here's a visualization of the new flow. The main thread is focused primarily on voting, while this thread 1 here is focused on processing incoming transactions and propagating them. And then there's another thread that is dedicated entirely to applying blocks. So what does this mean in terms of impact? For transactions, the impact is removed head-of-line blocking. Dedicating a whole thread for flooding allows for better transaction propagation, especially for higher throughputs. This also means we can do expensive cryptographic functionality like signature verification and hashing in the background. This saves us quite a bit of CPU time. This change also improves voting, since it also improves head-of-line blocking issues for votes, since votes aren't stuck behind transactions anymore. This also means that the node can process and propagate votes from other validators. Note that during application, the validators won't vote themselves yet. However, it can still process and propagate votes from other nodes. And in the future, we're planning to change this and allow validators to vote while application is happening. This is what I mentioned earlier about voting for ledger n+1 while we're applying for ledger n. So what are the advantages here? The first is better task isolation. Scoped independent tasks can run in parallel and not interfere with each other. A bonus side effect here is that to prevent data races, we refactored the code to better isolate various subsystems. This yields a better encapsulation of the code and leads to better interfaces. The second is that we have reduced head-of-line blocking across independent subsystems. So this first improves the global latency of the Stellar Consensus Protocol, and also improves latency of new transaction propagation, which allows for higher throughput. And finally, it removes long stalling on the main thread. So let's look at some results. As of today, we've already shipped some of this functionality and prototyped the rest. In simulated results, we were able to observe a 96% increase in theoretical Sorbonne throughput, as well as a 43% increase in classic payment throughput. So the results are pretty promising. We measured using a simulation framework called Supercluster, which is an open source simulation software developed by STF, and it lets you spin up artificial Stellar Core networks to do load testing on. So we use a small network of Stellar Core nodes for simplicity, and the synthetic Sorbonne payment load was generated across all nodes. We used a binary search to find the high sustained transaction rate, and sustained here means that the network can keep up at the transaction rate without dropping transactions for 10 minutes. And we compared the prototype against a previously released core build, specifically 21.3.1. So Just to give a glimpse of what future work looks like, here's how the flow would change when we pipeline voting and application. So this is before. This is what I just talked about. And this is after, where we can start voting for ledger n+1 while applying ledger n. So remember our color-coded votes from ledger n, which are the blue rectangles on the left? Those can now be done during ledger n-1. So by the time we apply ledger n-1, voting for ledger n is already complete. So we can start applying the block for ledger n right away. So next up, I'll talk a bit more about optimizations at the block application layer. So up until this point, the flow diagrams have shown transactions being applied in a single thread. But as I hinted at earlier, we can do better and parallelize Soroban. So first, I'll go over some requirements. So we need to respect an upper bound on runtime. Right? We need to close a ledger roughly every 5 seconds. So we can't take too long to apply transactions. And there are a minimum number of threads configured to apply Soroban transactions. And this is configured at the network level. Less cores on your machine are acceptable, but you risk falling out of sync. And this value will be chosen based on validator hardware requirements. We'd also like to prioritize transactions by the inclusion fee, even if that results in suboptimal ledger utilization. And this is a general philosophy of Soroban transaction utilization. We value fairness over maximum throughput. So the first and most interesting part of applying Soroban in parallel is building a transaction set that specifies how the transaction should be partitioned. This is possible because, as I mentioned earlier, Soroban transactions require you to specify every entry that will be read or written. And this is the transaction footprint. And this requirement makes it easier to parallelize Soroban. So I'll go over how to build these transaction sets and what they look like. The strategy to build the transaction set isn't part of the protocol, but the validation is. So what this means is that a validator can choose any partitioning strategy that they like, as long as they follow some key validation rules. The first of which is that you can't have conflicting reads and writes run in parallel, and I'll speak about that a bit more. And the second is that resource limits need to be respected. So, for example, our prototype at the moment uses a greedy algorithm that prioritizes by the inclusion fee and fills each thread to the sequential instruction limit. So it's essentially a bin packing problem where we fill up each thread until it's full. And because the strategy is not part of the protocol, we can optimize this without waiting for a protocol release. So here is visually what a parallel transaction set looks like. You have a number of stages, each stage with a number of threads, and each thread is just a list of transactions. Each stage is assigned a portion of the ledger's instruction count limit, with each thread able to run up to that limit. So for example, if the ledger has a limit of 10 million instructions, and you have 2 stages, each stage is assigned 5 million instructions. And what that means specifically is that each thread in each stage can run up to 5 million instructions. So each stage is run sequentially to handle read-write conflicts. So every thread in the stage must complete before you can move on to the next stage. Now, before I continue talking about handling conflicts, I'll quickly speak about what a conflict is in this context. Imagine that you have 2 transactions. One writes to an entry, and another reads from that same entry. If they are run in parallel on a validator, then no guarantees can be made about which one runs first. If the outcome or actual logic of the read transaction depends on it, if it observes the write, then we have a problem. Imagine that you have a read transaction that sends a payment. Thank you. Imagine you have, still work. Imagine you have a read transaction that makes a payment based off of some data, and a write transaction that's updating that data. If you run this on a validator in parallel, there are no guarantees about what the read will observe. And then the payment that's made off of that data could be different between validators, and this is unacceptable. So this is how we handle conflicts. To demonstrate why we use a stage structure, let's look at this example with only one stage. We have an Oracle transaction that writes a price entry, it updates a price entry, meaning it writes an entry. And then we have 50 transactions that read from that same entry. As you can see, all 51 transactions have to be run serially because of a read-write conflict due to that write. This is unfortunate because without that one transaction, the other 50 transactions could be parallelized. Now let's look at the same scenario, but with 2 stages. And now, as you can see, the Oracle write transaction has been moved to a different stage, allowing the reads to be parallelized. And we've seen that this stage mechanism works well for handling conflicts. Now, drilling down into what a stage actually looks like, the transactions are split into logical threads. But the only requirement at the protocol level is that conflicting transactions within a thread are not run in parallel. So in this image, imagine that none of the transactions in thread 1 conflict with each other. They could then be parallelized even more. If some of the transactions conflicted, you could identify which ones conflict, and let's call them conflict clusters, and run those clusters in parallel. So if you had additional cores on your machine, you could use this as an optimization. An example of where this could be useful is running a large-scale catch-up where you want to be run as fast as possible. You could use this optimization to identify the conflict clusters and use additional cores to make the catch-up run faster. And finally, it's important to note that there's no increased fee for a transaction that causes more conflicts. But we can change this later and surge price those transactions if we see the need to. So I've mainly spoken about building the transaction set because applying the set is relatively simple. You just spawn threads with the partition transactions and footprint. You collect the resulting modified entries and apply those changes to your database. Rent bumps, however, work a little differently, and they require some unique logic. Rent bumps write data, but they don't cause read-write conflicts. If you ever use Soroban, you may have noticed that footprints don't contain the keys for TTL entries, and this is by design. We didn't want rent bumps to cause conflicts in serialized transactions. So we allow multiple threads to bump the same TTL entry. We just collect all the bumps and reconcile them at the end, and this is easy because TTL entry values only move in one direction. They only increase, right? So this does mean that multiple transactions can pay for the same bump if they're run across threads in the same stage. But otherwise, rent bumps will work the same as they do today. So now let's look at some results. And please keep in mind that these are very, very preliminary numbers using a prototype with the benchmarks being run on my laptop. And the workload is also very specific. Each transaction is conflict-free. It's using 50 million instructions per transaction, and each transaction is reading 30 entries that are a kilobyte each. And we're measuring how many transactions we can fit into a ledger within a 500 millisecond apply window. So now taking the baseline as the number of transactions we can fit in this window, with one thread, we measured the increase in the number of transactions as we increase the number of threads. And as you can see here, as we increase the number of threads, we can fit more transactions into this 500 millisecond apply window, which is what we wanted to see, and the results look promising. So when can these features be used? Parallel transaction processing and propagation in the background is already available and can be enabled with the experimental background overlay processing configuration flag. For Q1 of 2025, we're aiming to add the ability to apply blocks in the background, as well as move more of the expensive transaction processing work to the background, like signature verification. And in that same quarter, we're aiming for a protocol change that would enable parallel processing of Soroban transactions. And in Q2, we'd like to remove all the experimental flags mentioned here and enable those features by default. And as I mentioned earlier, one of the changes we want to make in the future is parallelize voting on ledger n+1 while applying ledger n. This is the pipelining I mentioned earlier. And we also want to analyze the parallel Soroban usage to modify parameters and make improvements. That's all I had for today. Thank you.